Hello everybody. We have discussed the way we do Schrodinger mechanics. How do you try to solve quantum mechanical problems, what we can predict and what we cannot. And we have discussed in light of one particular problem. Let me remind you that we are dealing with only one type of cases, which we said that we are dealing with stationary states only. These are the cases where the expectation value of anything, any operator, doesn't change with time. Today, we will not work out any particular problem in quantum mechanics, rather rather have a general discussion on the potential problems. So let us start. Remind ourselves of the last problem that we are doing, which is the problem of infinite square well. So what was the problem of infinite square well? If you remember that, you are again dealing with piecewise constant potential here. So this is my x-axis, and I had these two boundaries in the x-axis. One is at 0, the other is at x equals to L. And we said that v equals infinity here, v equals infinity here, and v equals to 0 in this region. And we worked out what are the potentials for this problem. What are the wave functions, eigen functions for this problem? Remember that we did it. So this, if this potential, if I want to write this potential in algebraic form, I will write that v as a function of x equals v0 when x is lesser than equals L and greater than equals 0, equals 0 otherwise. Okay, but you see, what I choose as x equals to 0 is not of much consequence, so I request you to work out this problem in the following way. So Vx equals V0 at say x equals minus L to plus L. If I choose L by 2, it will be exactly the same problem, but that's why I have chosen minus L to plus L and 0 otherwise. So you should try to work out the same problem using this potential, which will look a little bit different, but physics of these two potentials are essentially the same. Now for these cases, what are the eigenfunction? We saw the energy is discrete, and eigenfunction, which I call Phi-n x t, with all its bells and whistles, that is, I have normalized the function, is this. And that's only in between, again, 0 to L and equals 0 otherwise. So when I want to state the eigenfunction, I have to state this entire thing. If I say that Phi-n is just this thing without stating that it has this functional form between 0 and L, that will be completely wrong, because outside that 0 and L, Phi-n is 0. That I have to specify. And remember that the energies So I have discrete energy states, and they are given by so this is the solution eigenfunctions that we saw. Also remember that because it is zero outside that potential well, so this has many names. So one name is obviously it's the infinite square well. Infinite because outside 0 and L the potential is infinity. Square because it goes to infinity almost discontinuously at 0 and L. It's also called a particle in a box problem because if you think of a box, the particle, the classical particle cannot go out of the box. So it's also sometimes called the particle in a box problem. The same thing is called in different names. Now outside the box, the potential is zero. Because of that, we called these as bound states. Probability of finding the potential rho xt, we called it pxt, right? So which is the probability density, and I can integrate that outside the outside 0 and L. So pxt outside the box is equal 0 in this case. Okay, that's why I called it a bounds, call these bound states. Now let me also remind you how the wave functions look like. So these are the wave functions, the first three wave functions. First three means n equals to 1, n equals to 2, and n equals to 3. The top parts are the wave function, and in the bottom we drew corresponding rho n's, which are essentially Phi-n mod squares. N equals to 1 state is the lowest energy state, is called the ground state. And then the n equals to 2 state is called the first excited state, because it's like if you don't give any excitation, then obviously everything wants to stay at the ground state. So that is the ground state, n equals to 1. And then n equals to 2 is the first excited state, n equals to 3 is the second excited state, etc. If we look at these wave functions with respect to the center of the potential well, the center of the potential well in this case is at 0.5, we see the n equals to 1 state is symmetric about the center of the potential well. So is n equals to 3 states. So both of them are symmetric. On the other hand, n equals to 2 state is antisymmetric about this potential well. So if it is positive in one side, we see a reflection where it is negative in the other side. So as you will see, if you try to draw all the other cases, n equals to 4, 5, 6, etc., all the cases where n is odd are symmetric, like n equals to 1 and 3 here, and all the cases n equals n even are antisymmetric. So the first excited state is an antisymmetric state. The third excited state is an antisymmetric state. Second excited state is a symmetric state. Fourth excited state is a symmetric state. And remember that fourth excited state means n equals to 4 plus 1, 5. We also see between 0 and L, here between 0 and 1, apart from 0 and 1, in between 0 and 1, if I look at the ground state, n equals to 1 state, the wave function never gets the value 0. So it doesn't have any node between 0 and 1. N equals to 2 state has one node, n equals to 3 state has 2 nodes, and if you go to higher n's, you will see that any state has n minus 1 nodes. So what have we learned? N equals to 1 we called ground state. Even n, the wave function is antisymmetric, odd n, the wave function is symmetric, number of nodes so this is number of nodes in the well, inside the well, is n minus 1. The first one did not have 1, the second one had 1, etc. Okay. So n equals to 1 is ground state, n greater than 1 are excited states. Okay. The next thing is that if I take phi m xt, say the complex conjugate of that, and I take n xt, integrate that over all x. In this case, the all x integration will again mean integration from 0 to L. This is equal, so this I write still all x, but remember that outside 0 to L it is 0, so you have to just integrate over all 0 to L only. So this is delta mn. So this again is your homework to check this. So for this, what you have to do, to check this, what you have to do is take m equals to n. So this will just become phi n mod square, and phi n, you put the value from here. You see, when you take mod square, the exponential part will not come. It will only, the integration that you have to do is of a sine square x. Do the integration and see what you get. So you'll see that you will get 1. In the other case, where it is not, m and n are different, then you will see that you will get 0. Okay. So let me not do these things and keep this as a homework for you. Okay. Fine. One more important thing about this is that, remember, we said that if we are not measuring, then any wave function, this is now not an eigen function. Phi m, psi n, these are eigen functions, energy eigen functions of this particular case. So these are energy eigen functions of the energy operator, right? Now if I want to measure any other dynamical variable, so what I should do is to start with the wave function before the measurement, can be anything. But it should also be written, you should also be able to write this in terms of the eigen functions of the energy operator. And since I know the eigen functions already, which are psi n's, so I should be able to write it this way. Okay. Now, it is not guaranteed that you will always be able to write it, but this solution is something that allows that you will be able to write any function in terms of this summation. Any function which is so this is a function which is a solution of Schrodinger equation. For the problem. Obviously, if it is not a Schrodinger solution of the Schrodinger equation for this particular problem, we don't bother about it, because of the solution of Schrodinger equations are only the allowed wave functions. So this is any solution of Schrodinger equation for this problem should be I should be able to write it in terms of linear combinations. So this is called linear combination of my energy eigenfunctions. The fact that I will be able to write it in this way is called completeness. Okay. So these eigenfunctions form like in vectors we learned that there are unit vectors in different directions. These eigenfunctions, these unit vectors are also called eigenvectors, right? These eigenfunctions are like the eigenvectors, and there are infinite of them. You can see n goes from 1 to infinity. And any function I should be able to write in terms of some constant times those eigenfunctions. Just like some constant times the eigenvector, if I write, then I get my total vector back. So fact that I should be able to write in terms of these eigenfunctions is called the completeness. Okay. Now why? So one reason why this is I will be able to write this is because of the nature of the Schrodinger equation. So the Schrodinger equation, if I write it here, so this psi is any psi. It's not only the eigenfunction psi. You see, so this is in general. I'm not only writing for the stationary states. In general, you see, this equation is linear in psi. So what do I mean by that? I mean that there is no psi square or psi cube or anything other than psi to the power 1 appears in this equation. Okay. So if that happens, then what one can do is one can find a solution psi 1 and psi 2. So if they are solutions of this equation, then you can check that psi, which is equals to psi 1 plus psi 2, will also be a solution. Okay. And you can even multiply this by some a1 psi 1, or let us, because we are going towards that, let's call c1 psi 1 plus c2 psi 2, and still it will also be a solution. Okay. So that is what we are doing here. That we have come to know that each of these psi n's are solutions of the Schrodinger equation in case of this infinite square wave potential. So any solution of the infinite square wave potential you should be able to write down in terms of these eigenfunctions. Okay. So let me leave it there, because if I go any further, it will make things even more complicated. But it's a mathematical thing, and so such eigenfunctions belongs to a certain class of functions. But let us not go into those complexities here. If you want to know more, we can discuss it outside the class. Okay, let's proceed. And let's now discuss. So this is all about the particular problem that we have done, where we had an infinite square wave potential. So let us discuss about potentials in general. And so one type of potential which doesn't look quite like infinite square wave but has certain properties of infinite square wave is everybody's favorite potential, is that of the harmonic oscillator. And you will see that reference to this comes back again and again, and there is a very good reason for that also. I request you to think about it. Why one talks about harmonic oscillator potential so many times? And this is like half kx square, right? So what I will do is I will consider k equals to 2 and try to plot this potential. You should also try that by yourself. So this is the harmonic oscillator potential. It goes to 0 at x equals to 0, and then if I go to very large x, it becomes infinite. If I go to very small x, it becomes infinite. I have only plotted between -2 to +2 here. Okay. What is the value of this potential at x equals to 1 and x equals to -1? Well, we are talking about, so x to the power n, where n is square, right? So it's half kx square. K I have taken 2. So it's just x square. So n equals to 2 is the case here. So Vx equals x square. So if x equals to 1, obviously x square equals to 1. So at x tends to plus or minus infinite, Vx also tends to infinite. At x tends to 0, or x equals to 0 rather, Vx equals 0. So this is also the case quite like the potential well. So in the potential well, the x equals to 0, because the potential well was not symmetric about x equals to 0. It was symmetric about x equals to 0.5. But at x equals to 0.5, the potential is 0. It's essentially 0 from between 0 to L, or 0 to 1, if I have taken that L equals to 1. But at plus minus infinity, x plus minus infinity, that potential was also infinity. Now one can visualize the infinite square well potential in the following way. So here, as you can see, what I have done is I have plotted different values of different potentials for different values of n. X equals to n equals to 2 was the parabola. But then we go to n equals to 4. What happens is that all of these potentials, obviously, because it is just mod x whole to the power n, at x equals to 1, all of them have value 1. At x less than 1, as I go for larger and larger n, the value of x to the power n at x less than 1 decreases, and value of x to the power n at x greater than 1 increases. So what happens is, essentially, when I go to, you can see here, n equals to 100, it looks almost like an infinite square well. So just you go to a little bit away from 1 in the positive side, or little bit negative from -1 in the negative side, the potential takes very large values. So if I could have plotted n equals to 10,000, say, it would have looked almost like our infinite square well potential. At 100 itself, it looks quite like that. Okay, the other potential we discussed is Vx equals mod x whole to the power n, where n is very large. Now for these potentials also, this is true. At Vx tends to plus minus infinity, the potential also goes to infinity. Sorry, at x tends to plus minus infinity, the potential also goes to infinity. Now let us look at a different type of potential. So again, let me draw my x-axis here, and say this is x equals to 0. So say this is x equals to minus L, and this is x equals to plus L. So I have still a piecewise constant potential. The value of the potential is somewhere here. So y-axis I am plotting either V or E. Okay. So here the potential is V equals V0. And again the potential is V equals some finite value V0 here. And in between the potential is 0. Okay. Now this is different from the infinite square well. What can we say? We can say this is a finite square well because the potential doesn't go to infinity anywhere now. Now to solve for a given problem, remember we are still doing stationary states, which are eigenstates of the energy operator. So I have to talk about a particular energy. Now let us see what is the energy. Energy consists with the kinetic energy, which I write with Ke, and the potential energy, right? Now the nature of the kinetic energy is such that it is always greater than zero. Kinetic energy can never be negative. And if you remember that for a particle, if I believe in special relativity, even when the particle is at rest, it has an energy of mass, if its mass times c square. So kinetic energy is never zero; it's always positive. If you are not dealing with not dealing with the relativistic particles, you can say that okay, the kinetic energy is zero, but it can never be negative. The potential energy can be negative or zero also, which essentially means that the total energy has to be always greater than the potential energy. Because with the potential energy, the kinetic energy will always add something because it's greater than zero. Right? So this is always true. Now let us ask the question, what happens if my energy, let me draw the potential again here, and I am drawing it like this. So this is essentially the value of the potential plotted in a graph where my x-axis is x, the y-axis is the potential. Okay, why don't we make it a solid line like this? So this value is V0 here. So let's say that I have a case where E is less than V0. So my energy is somewhere here. Classically, what will you say? We will say that the particle, say the energy is less than V0. Particle cannot be either here or here, because if the particle is there or there, so then I get an energy which is less than V0. In the region 1 and 3, if you wish, the particle cannot be there classically, because if the particle is in region 3, for example, in the region 3, E is less than V0. V0 is higher than E. So that is not possible because always the energy is greater than the potential energy. So classically the particle can only be in this region again, in between, say, if I wish, say 0 to L, if you wish. Particle will always be in between 0 to L. So this is again an example of bound states. Now let me remind you, when you write down the Schrodinger equation, then we define this quantity, these things called K1 square, which is the case when E is greater than V0. So this is for E greater than V0. And we defined K2 square, which is when E less than V0. And we said that corresponding to K1, I will get PHY-1 x. We're writing only the x part of the solution now, is like, so this goes as e to the plus or minus ik1x. These are, like, if you wish, writing things in short forms, just like something to remember here. And these are e to the plus or minus, these are exponentials now, so these are k2x. Okay. So E less than V0, which is region 1 and 3 here, I will have solutions which are exponential. And in the region 3, you see that I can have either exponentially rising solution or decaying solution. Rising when I have plus sign. If I have plus sign, then as x increases, the phi also increase. But that cannot happen in region 3, because in that case, it will eventually go to infinity at x tends to infinity. So region 3, the solution, so if I now try to guess the solution, in the region 3, I should have some type of exponentially decaying solution. So this is e to the minus k2x. Region 3, remember, E is less than V0, so we are looking at k2 and phi 2. Similarly in region 1 also, but region 1 x minus infinity will make at x minus infinity, if I take the exponentially decaying solution, x minus infinity, it will go to infinity. So I need an exponentially rising solution in region 1. And in region 2, I will have solutions of type phi-1, and it will be like the solution we had in infinite square well. So region 2, I will get a solution like this. So when you do the matching at the boundary, you will essentially end up with the ground state of this type of potential, which looks like this, which doesn't go to 0 at x equals to 0 and x equals to L, like in case of the infinite square well. But more or less the particle stays in between 0 and L. There is a little probability that you find the particle there and find the particle there, but very little probability. Probability goes to 0 as you go very far away from the potential well. So these are still bound states, but the states kind of bleeds a little bit outside the well. Okay, now let us see what happens when E is greater than V0. Now, just for the sake of understanding, let me change the potential a little bit. Let us not call the 0 and V0. Let us just draw it in the following way. So I draw the potential, exact same thing. We'll see that if doing this, our understanding will be easier. What is happening? So I call this as 0 and call this as minus V0, which is absolutely fine. I have just added minus V0 to the potential, which I was drawing earlier. Okay. So this is my x-axis. And now I consider my E is greater than 0, which essentially means the potential is outside. The energy is here above. So in this case, that will correspond to energy which is there in that line. I am not drawing it, otherwise it will confuse you in this particular. So let me still show you. So the potential will be here, which is the E greater than V0 case. So in this case, what happens? So what is it physically? Physically, this means the following. Imagine there is a particle coming from the left hand side. Okay. So at x tends to minus infinity, it's a particle. Let me first write a particle coming from left. Okay. So at x tends to minus infinity, the particle doesn't see, the particle is free. I'm writing it with an inverted comma because a particle in quantum mechanics is never free. Whenever it sees any potential at any x, but at x tends to minus infinity, the potential is 0. That's why I call it a free particle. Something happens, some interaction happens at x in between 0 to L. So this is, say, x equals to 0 and x equals to L. In between that, there is some interaction happening with the particle, interaction between the particle and the potential, because the potential is minus V0 here. Okay. Then the particle goes to plus infinity. X tends to plus infinity. Again, the particle is free. Okay. So this physically, if you think of in classical sense, what is happening here is that potential, if you wish, is given by some, say I have a nucleus. So I have some positive charge here, say a proton. An electron is coming from there and is doing this. So the electron is here when it is very far away. The electron is not seeing this potential, because remember that the potential for a proton will be minus 1 by r at very large distance, r very large. The potential is essentially 0. So the electron is like a free particle here. When it comes near, so let's say that in this region, the interaction happens. So that is the region between 0 to L, if you wish. Obviously, the potential is different. The system is not quite the same, but the qualitatively it is similar. And here, when again, so this is like minus infinity, and this is like plus infinity. Again, you see the electron is moving like almost like a straight line. So this is, again, the particle is free. So this is the case of scattering. If I consider these as alpha particles and this as the gold nucleus, then this is essentially Rutherford scattering. If you consider these as photons and this as an electron, this is the Thomson or Compton scattering. So these examples where the energy of the particle always remains greater than the potential is the case of scattering. Okay. So these are called scattering states. So we talked about two types of states. So this is the finite square well case. So 0, V0 minus V0. If the energy is here, this will correspond to a bound state. And if the energy is here, this will correspond to a scattering state. So such problem allow both type of solutions, bound state and scattering state. Such potential allows both type of solutions. But there are some extreme cases. One we have already seen. If the energy is lesser than the potential at plus or minus infinite, plus and minus infinite, we only get bound states. So this is only. So just like the case of harmonic oscillator, where at plus minus infinity, the potential was infinite. So the energy, if I have a finite energy state, it is always less than infinite. So that is where you only get bound states. Again, the infinite square wall, you only get bound state. If on the other hand, the energy is always greater than the potential at plus minus infinity, you will get scattering state. Like this problem. Okay, so these are conditions of extreme potential. So let me give you a concrete example, and this is just you have to take my word for granted for this particular example. So this is because I will not be able to show you why the potential looks like this, and this is the potential of hydrogen atom. The hydrogen atom potential, hydrogen atom is a three-dimensional problem, and it can be reduced to a one-dimensional problem where the potential looks like this. Okay, so this here at x equals to 0, the potential value is infinite, and then at certain x, which corresponds to the radius of the ground state of the hydrogen atom, or the Bohr radius, you get a finite negative value for the potential, and then you get other values. So this corresponds to minus 13.6 electron volt of energy, and then you will get this n equals to so let me, the drawing will not be proper, so I don't want to level a n here, but you get the other excited states of the hydrogen atom. So 13 minus 13.6 is the ground state, as you know, for the hydrogen atom. So these are all bound states. But then I can have an energy here which is greater than 0, and say, let's say electron volt, because that's the unit we are using. So that will be a scattering state. Because you see, in this case, the energy is greater than the potential value at infinity, positive infinity. The potential value is infinite. I did a mistake here. I'm not plotting against x, obviously. In case of hydrogen atom, we are plotting against r, the distance from the nucleus. Okay, so having said that, let us see that what type of potential examples we will do in the next two classes. Examples. Before I go to the first example, let me tell you a similar thing that happens in optics, because optics is also wave phenomena. They are quite related. So in optics, you know that if I have two refractive medium, so this 2 has refractive index n1 and n2, then what happens? So light falls into it. This I call, say, incident. There will be a reflection, and some of the light will go in, so that I call transmission. So this is what happens. If this medium is transparent, if the medium is opaque, then I can have incidence, I will have reflection, and there will be transmission, which also sometimes called absorption, right? Because the light does not go very far in this opaque medium. Like if you wish, if you have a mirror, light falls into it, most of it is reflected. Nothing goes inside because it's an opaque medium. Mirror means mirror backed by some mercury or silver. But if you just have a glass slab, then there is transmission. Now the corresponding quantum analog for this problem is the following. So let me draw the potential as always. The potential is, so let me draw the potential with blue. Potential is, say, till x equals to 0, it is 0. And then here it is V0. At x equals to 0, the potential changes. Okay. And consider the energy, which is somewhere here. So you see immediately, this is a scattering state. And the energy is greater than V0. So then I will see the first type of case. So then I will see the first type of case. The other example can be exactly the same potential. But now my energy is less than V0. Okay. Now, let us discuss a little bit what we expect to see in these two cases. Okay. These two belongs to the same example. We will see one more example at the last class. So let us discuss a little bit what we expect to see in these two cases. Let's start with the first case first. Here we will be talking about particles coming from the left, just like we discussed when we discussed scattering. So particles coming from the left. And as we said, at very large distance from the potential. So these are called potential barriers, just like mirrors. So barriers means that you have two different potentials in either parts of the barrier. So for the potential barrier, if the particle is very far from the barrier in the left hand side, in our potential case, the particle is essentially a free particle. And the free particle wave function is either written by e to the ikx or e to the minus ikx. Okay. Now we are considering a particle coming from left. So let us first check which one of these corresponds to particle coming from left. So for that, what I do is I call this phi plus and call this phi minus. Okay. So phi plus, when I operate this on phi plus, what will I get? I will get ik outside and remember that p hat is what is p hat? Let me write it here, minus ih cross del x, right? So I'll get that minus ih cross and then I will get back phi plus. So this is, so p hat phi plus is minus, cancels with I square, so I get k h cross phi plus, and kh cross is p, so let's call this p0. So that is the momentum of the particle. On the other hand, if you do this, if you try this minus phi minus, you will get that you will get minus p0 phi minus. So this corresponds to phi plus corresponds to a particle coming from left, and phi minus corresponds to a particle which has the opposite momentum, which is a particle going in the minus x-axis. So phi plus momentum along x cap, phi minus along minus x cap. Okay, just want to I want you to remember these two. Now, so this is the boundary. So at x equals to 0, here I have potential V equals V0. Here I have potential V equals 0. And remember that we are dealing with case where E is greater than V0. Okay. So E is greater than V0 means that if I go back a little bit now in our earlier discussion today, E greater than V0, the solutions are of PHY-1 kind. So I can have e to the plus ikx or minus ikx type of solution. And we have seen that plus ikx corresponds to particle coming from left. So first I will have the particle coming from left. This will be a wavy solution, and so this is e to the I kx. What is k? K square is, so let's call this k1 in the region 1. So k1 is in the region 1, 2m by h cross square. So this is region 1. E minus V0, I don't have V0 is 0 here. The region 2, okay, so first let's complete region 1. Now this is coming in the region 1. But you see, region 1 can also have a solution where the particle going this way, and this we interpret just like the optics case as the reflection. So this is incident, this is reflection. Okay. So region 1, then psi in the region 1, and I'm writing only the x part now, will be some incident which will have some amplitude which we still don't know what it is. Then ik1x plus reflection e to the minus ik1x. Okay. What about region 2? In the region 2, you will get again, so something will get transmitted, so I will get in this direction. Will I get anything in this way? Well, this way if I write, so in the region 2, so I will definitely get a transmitted wave which is going in the positive x direction. So let's write this way. Ik2 now, x, and k2, you can imagine what it is. It's k in the region 2, which is 2m by h cross square, e minus v0. Now v0 is not 0. But will I get a e to the minus ik1x? Well, that will mean that something is coming from the right hand side to the left hand side. But if the only type of particle we are dealing with is the incident is from the left, so then this is not there. Because just like the problem in light, you are considering how much is of the particle getting incident from the left is getting reflected or transmitted. So that is the question we are asking. How much of the particles incident from left are reflected or transmitted? How much is reflected? How much is transmitted? That is the type of question we will ask for this particular case. Okay. Now, I will give you another homework is to work out what will happen in this example. In this example, in the right hand side, you see it's the type 2 solution where my E is less than V0. So I request you to figure out what will be these two. So this thing is not there. Okay. So what will be these two solutions? So this is the case where E is greater than V0. For E lesser than V0, what will be these two solutions? So I request you to figure that out. These are the things that we will discuss in the next lecture. So region 1, E greater than V0 is already, we have discussed the two solutions. Region 2 is what you have to figure out. Okay, so I'll stop here and we'll take it up from this case from here in the next class.